Hello everybody. Okay, let's continue. If you have any questions, please write them down into the chat. Okay, our next topic, one of the main topics of this course, is the limit of the sequence. Sequence. Definition. A function f that is from n to r. That means this function has a domain of this function is this set, and it attains values from that set. Not all of the values, so codomain of this function is not necessarily all of real numbers. It's impossible. We will prove this later. But it is inside. Let me write it down. Whose domain is the set of natural numbers, not integers. Natural numbers and codomain is a subset of real numbers. Is called a numerical sequence. Notation. This is a sequence, and that would be xn an element of this sequence, one of the numbers that this sequence attains. Note that this sequence could, like for any natural number, there should be exactly one corresponding real number, but no other restrictions. So we can use the same real number many times and so on. So, okay, let me write it down here. This is the sequence. This is an element of a sequence. Now, one very important definition, one of the most important definitions, and I'm saying you this in advance, that not knowing this definition on the exam is immediate failure of the exam. So this is one of the important ones. Definition. A number A, real number, is called a limit of a sequence xn if for any positive number epsilon there exists a natural number, capital N, natural number. This capital N, generally speaking, well, of course it is, depends on epsilon. And just to emphasize this, I'm going to write down over here subscript epsilon. It is not necessary, this little bit, because I declare this new variable after I declared epsilon, so generally speaking, it does depend on epsilon, even if I didn't write it over here. So there exists capital N such that for any natural small n greater than capital N, n is also a natural number, it follows that x n minus a absolute value is less than epsilon. So this is the definition. If this definition, well, if this is true, then we will say, oh, no. Good enough. We will say that we will write this down. This statement, we will say that a sequence xn converges to A, or we will say a sequence xn tends to A, and we will write limit of a sequence xn as n tends to infinity equals A, or we will write xn just tends to A, well, n tends to infinity. Definition. Yeah.
Is it important to write plus or minus something?
Yes, it kinda is. Let me. Неудобно. Plus infinity. Actually, we will see later then that well, when we discuss a definition of a limit of a function later, it will be in maybe 3 weeks-ish. We will discuss like different limits as argument of the function tends to different numbers. And there will be a more general formula into which this formula kinda like sticks. I mean, this would be one of the cases. Let me say it like this: one of the cases of this general formula. When we discuss a limit of a sequence, the only thing that n can tend to is plus infinity. There is no other choices. So this is kinda redundant so far. It looks redundant, but it would not be the case later for the function. I will sometimes forget to write n tends to plus infinity, but this is just my forgetfulness. This is not like strictly correct. I will try to not do this during the lectures, but I will do this a lot during the seminars. And you are also okay to, well, free to forget this bit only when we discuss limit of a sequence, because there is no other option. Thank you for your question. Any more questions, guys, from the chat? Покажите, пожалуйста, сколько у нас, в принципе, присутствует в Zoom людей. Сколько там? 24. Хорошо, хорошо, нормально. Хорошо. Moving on. Moving on. Definition. A sequence having a finite limit is said to be convergent. Otherwise, it is said to be divergent. Let's look once again to this definition that we have here. Поверните, пожалуйста, камеру. Камеру поверните, пожалуйста, чтобы это видели. This definition over here. Here I say that this limit, this future limit, a, is a real number. That means that it is a finite number, not infinity. Later we will construct a definition of a sequence tending to infinity, to different kinds of infinities. And it will be like a slightly different definition. So if this statement holds, then the sequence is convergent. So far we only have convergent sequences. But the limit should be a finite number. Okay, let's move on. Let's discuss an example. Let's prove by definition that a limit of, as n tends to infinity, of a sequence 1 over n is 0. Let's see, what should I do this? What should I do with this? Let me write down the definition. For any epsilon greater than 0, there exists capital N, depending on epsilon, such that, natural number, such that for any n greater than capital N, it follows that the term of my sequence 1 over n minus the limit 0, absolute value less than epsilon. Now, I want to prove this. I want to say that this is true. Let me start by solving this inequality. I'm solving this inequality. Well, 1 over n, well, first of all, we ignore 0. Then 1 over n is a positive number. Then we throw away the modulus. So we have 1 over n less than epsilon. And this is, of course, the same statement as epsilon 1 over epsilon, write it down like this, n greater than 1 over epsilon. Okay, so the solution of this inequality is n greater than 1 over epsilon. Now, I want to construct a number capital N such that for any small n greater than capital N, this is true. One of the ways to do this is make capital N greater than this number. If so, small n is greater than capital N, which is in turn greater than 1 over epsilon. Hence, small n will be greater than 1 over epsilon. First of all, I don't really need to make a formula for this capital N. I want to prove that it exists, but I don't really need the formula. And proving its existence is really easy. Look, I just want to find any number, natural number, greater than this specific number. This is possible always just because a set of natural numbers is not bounded above. We discussed it last time. A set of natural numbers is not bounded above. So for any specific real number, for example this one, there is a natural number that is greater than this real number. So its existence is really easy to prove. But in this simple case, I can even write down an express formula. So I'm constructing a number capital N, which is greater than 1 over epsilon. I will take 1 over epsilon integer part. This is a number that is, this could be smaller than 1 over epsilon, but not too much smaller. So it is, the difference between those two numbers is between 0 and 1, as we discussed last time. So if I added over here plus 1, then this number would be an integer number greater than 1 over epsilon, strictly greater. One last bit of this construction is over here I asked this number capital N to be a natural number. This number is not necessarily a natural number. It is possible, is it possible? But let me think about it. No, this is okay, this is totally okay. Epsilon is a positive number, so this is a natural number. Yeah, this is possible, this is okay. Okay, so this number, as I have discussed, is greater than 1 over epsilon. Since small n is greater than this number, I can write down somewhere, let me write it down over here, that for any n greater than capital N, which is in turn greater than 1 over epsilon, it follows that n is greater than 1 over epsilon. And from here it follows that this part, 1 over n minus 0, absolute value less than epsilon. And thus I proved that the limit of this sequence is indeed 0. Any questions so far? Guys, please in the chat write down that either that this is clear or write down your questions. Any questions? Okay. Okay, moving on. Здесь There are a lot of similar exercises, examples. We will discuss them on the seminars. Let me write down something maybe. Oh no, I should discuss it on the seminars. Okay, moving on. Moving on, definition. A sequence xn is said to be bounded if there exists a number m, real number, such that for any natural n, it follows that xn is less absolute value. Absolute value? Yes, less or than n. Yeah, like this. So this is really just a the same definition as a bounded set. So if we look at this sequence as a set of real numbers, then this set is bounded exactly in this case. Okay, theorem. A convergent sequence is bounded. Proof. Since this sequence is convergent, let's write down the definition of a convergent sequence. So there exists a number a, as we said. Yeah, so once again, the sequence is convergent if there exists a finite limit. So I'm writing down there exists a real number a, and then I'm writing down the definition of a number a being a limit of a sequence xn. For any epsilon greater than 0, there exists capital N natural such that for any n greater than capital N, it follows that xn minus a is less than epsilon. Okay, now here it says this is true for any epsilon. I'm going to choose any specific number epsilon. For example, let epsilon be equal to 1. Then for this number epsilon, there exists capital N, there exists n, such that for any n greater than this capital N, it follows that xn minus a is less than 1. Let me open this modulus. It means that xn minus a is less than 1 but greater than minus 1. Okay, but this means that xn is less than a plus 1 but greater than a minus 1. Okay, and this is true, this statement is true for any n greater than capital N. Okay, so there are exactly capital N terms that we did not cover by this statement. So the first capital N terms could be any terms, but starting from the capital N plus 1, terms of our sequence satisfy this inequality. Okay, let me construct a number, capital M, which would be a maximum of x1, x2, and so on, x capital N, and so on, a plus 1. Then, for any number n, natural number, it follows that xn is less or equal than capital M. Let's see, if small n is not greater than capital N, then it is one of those numbers, the first here. Then, of course, this capital M, which is a maximum of those numbers, is greater or possibly equal than xn. And if small n is greater than capital N, then by virtue of this statement, this is also correct. Okay, and in the same way, let small m be minimum of x1, x2, x capital N, a minus 1. Then for any n, follows that xn is greater or equal than small n by the same proof, the same analogous proof. Okay, but this means that the number xn, the set of numbers xn, is bounded above. Here it means bounded above. And this means that this set is bounded below. Okay, very well. Now, by taking a absolute value of capital N and small m and taking maximum of those values, we can construct a number for this definition. But I think this is already clear that it is possible. Let me do it anyway, let me do it carefully, but I think it should be already obvious that this is possible. Okay, let I will call it C, capital C, be a maximum of absolute value of m and absolute value of m. Then for any natural, it follows that xn is less than capital M, less than small m. Capital M is of course less than absolute value of capital M, and small m is of course greater. This is wrong. Not like that. Okay, if xn is positive, then then capital M is positive and xn is less than capital M absolute value. And if xn is negative, then by virtue of this inequality, xn is less or equal than small m absolute value. And from here, it follows then xn is less or equal than maximum of small m and capital M, which is called C. So there indeed exists a real number such that absolute value of xn is less or equal than this real number for any n. That means the sequence is bounded. Okay, any questions? Why xn is less than absolute value of m? This is for negative xn, if xn is negative, and this is for xn is positive. So we have two cases, either this number is positive or negative. If it is positive, then we just add absolute values on those two positive numbers and everything holds. And if it's negative, we have I think it will be better to write like this. Like this is better. So if xn is negative, then this necessarily means that small m is negative. And if we add absolute values to those numbers, absolute like modulus put over here and over here, then we are multiplying both of those numbers by -1, which means that the sign changes, the sign of inequality. Okay, any more questions? Moving on. Next, also very important theorem, theorem 2. About uniqueness of a limit. A sequence cannot have two different limits. Proof. Okay, it's time to take a break. Let's prove it after the break. 5 minutes break. And if you have any questions, please write them down in the chat. Okay, moving on. Proof. So suppose there is a sequence that has two different limits. Let A1 be a limit of a sequence xn and A2 be a limit of a sequence xn. And A1 is not equal to A2. Two different limits. Suppose there exists such a sequence. Okay, since A1 is not equal to A2, since A1 is not equal to N2, let's fix two non-intersecting neighborhoods of A1 and A2. Let me remind you over here, let me remind you, a neighborhood epsilon neighborhood of a number A is a open interval from A minus epsilon to A plus epsilon. And since there exists, those two numbers are not equal to each other, A1 and A2, I can choose the sizes of those neighborhoods small enough that those neighborhoods of A1 and A2 do not intersect, like that. So this picture is not a part of the proof. I will continue writing the proof over here. This is just an explanation. Okay, let epsilon be a number, positive number, equal A1 minus A2 absolute value divided by 2. So exactly 1/2 of the distance between A1 and A2. Then epsilon neighborhood of A1 and epsilon neighborhood of A2 do not intersect. Its intersection is an empty set. Let me draw a picture once again. So this is A1, this is A2, and epsilon is exactly 1/2 of the distance. So a neighborhood of A1, epsilon neighborhood of A1, is this interval, and this point is exactly one like middle point between A1 and A2. And epsilon neighborhood of A2 is this interval, and they do not intersect. They are like touch each other at this point, but this point does not is not included in either of those sets. So those two do not intersect. If you are uncomfortable with this touch, you can choose even smaller number epsilon, and they will not even touch. This is not important right now. Okay, so I found two non-intersecting neighborhoods of A1 and A2. Yeah.
Can I ask, do we have to prove that there are such neighborhoods that don't intersect?
This is the proof. I have given you the proof over here. Once again. Yes, once again. I explicitly gave you a size of this neighborhood, of those two neighborhoods.
This is enough for proof.
Yes. Once again, let me show you once again. I explicitly constructed those two neighborhoods. Let me write them down. This neighborhood is from A1 minus epsilon, which is not important, to the right endpoint is A1 plus absolute value of A1 minus A2 divided by 2. And this is from A2 minus this same number divided by 2 to A2 plus epsilon. A2 plus this same number. And you can check that those two numbers are the same. You can check that they are the same. So this is the picture that we will have. Two touching open intervals. They do not intersect. Guys, is it clear? Is it clear? Please write down your questions if it's not clear. Okay, we have two non-intersecting neighborhoods. Moving on. Now, we know that those two numbers are limits of our sequence. Let me write down those two definitions. So, A1 is a limit of sequence xn, means for any epsilon greater than 0, there exists a number n. I'm going to call it n1. I will explain why later. Such that for any small n greater than n1, it follows that xn minus a1 absolute value less than epsilon. And the second before I write down the second, from here, look, this statement, this bit over here, this is the same statement as xn being, not wrong, but not clear. Let me think about it a bit. So this is correct for any epsilon. Let's choose this epsilon over here. I will put this number epsilon over here. For this number epsilon, there exists such a number n1. Let me write it down. Let epsilon be equal to a1 minus a2 divided by 2. There exists number such as n1, such as all of this, and this statement is, of course, means that xn is less than a plus epsilon and less less than a minus epsilon, like that. This, of course, means this is the same statement as xn being inside of epsilon neighborhood of A. Can you see? Is it clear? Guys, is it clear? Okay. So if this is correct, then I will write the same statement about A2. For any epsilon greater than 0, there exists n2 such that for any n greater than n2, it follows that, well, basically the same statement here, xn minus a2 less than epsilon, but this statement by the same virtue is the same as xn is from epsilon neighborhood of a2. This was a1, this is a2. A1 over here. Okay, okay. So now, let me move over here. So now, starting at number n1, all of the terms of my sequence is inside epsilon neighborhood of a1, and starting from number n2, all of the terms of my sequence is inside epsilon neighborhood of a2. Okay. But then taking some number n, small n, greater than maximum of n1 and n2, we can see that this number satisfies both of those conditions. It is greater than n1 and greater than n2. We will have xn is inside epsilon number neighborhood of a1 and epsilon neighborhood of a2. But this is impossible. Okay, let me finish and then I will explain again. But this is impossible since we constructed those neighborhoods to be non-intersecting. Which is impossible. Since those neighborhoods end of proof. Okay, so let me just explain once again like geometrically, and then I will go once again over the proof. So geometrically speaking, this is not a proof, this is an explanation. On our number line, suppose we have two different numbers which are both limits of my sequence. So I have a1 and I have a2, two different numbers. I'm going to construct two neighborhoods of A1 and A2 small enough that they do not intersect, like this. Like this. The statement, let me write down once again a limit of a sequence xn being number A. This means for A in epsilon greater than 0, there is this capital N, such that for A in N greater than capital N follows xn minus A less than epsilon. This last bit is the same statement, this last bit is the same statement as xn being from epsilon neighborhood of A. Lilas and Onur, please confirm that you understand this little bit, that this statement, this inequality, is the same as to say xn is from epsilon neighborhood of A. Is it clear for you too? Okay. Now, this definition of a limit says that starting at some point, starting at some number of at our sequence, all of the terms starting at some numbers, all of them are inside this neighborhood of A. So, since A1 is a limit of our sequence, then starting at some point, all of the terms of my sequence are inside this neighborhood, somewhere over here, like that. On the other hand, since A2 is a limit of my sequence, all of the terms should starting at some point, maybe different point. So starting point for this limit and this limit could be different numbers, but anyway, starting at some point, all of the terms of my sequence is inside this neighborhood. Now, I'm taking a number, this is a number of the term in my sequence, greater than both of those starting points. Then the corresponding term of my sequence should be simultaneously in this neighborhood and in that neighborhood. But this is impossible since they do not intersect. Okay, is it better now? Okay, but once again, the proof is not this. This is not a proof. This is a picture. This is an explanation. Okay, any more questions? Any more questions? Okay, moving on. Next topic is passage to the limit and inequalities. Passage to the limit and inequalities. One interesting note. A little bit of language note. guys, over here I gave a definition. A number A is called a limit, and so on. Taking into account this last theorem, there cannot be two different limits. So if there is a limit of a sequence, it is the limit of a sequence. So over here, this definition, over here, this A could be actually the limit of a sequence. Not really important, but just a note. Okay, moving on. So, theorem. Let a sequence xn tend to number A and sequence yn tend to number B. And also let A be smaller than B. Then there exists a number capital N such that for any small n greater than capital N, it follows that xn is smaller than yn. Geometrically speaking, this is very understandable. Look, let me draw a picture once again. So we have two numbers a and b, and sequence xn goes over here, xn tends to a, and sequence yn tends to b, goes like that. The idea is very similar to the previous proof. I'm going to choose small enough neighborhoods that they do not intersect, this neighborhood of A and that neighborhood of B. And starting at some point, all of the red dots, terms of xn, is inside this neighborhood. All black dots, terms of yn, is inside this neighborhood. So starting at this point, any xn is less than corresponding yn. Let me prove it carefully. This was theorem 2, this will be theorem 3. Proof. Choose a number C such that A less than C less than B. For example, I can choose its average of A and B, arithmetic average. Of course, there exists such a number. By definition of a limit, there exists number n1 such as for any n greater than n1, it follows that xn minus a is less than C minus A. Look, C is greater than A, then it means C minus A is a positive number. For any positive number, there exists such a number capital N, starting from which all terms of our sequence satisfy this inequality. Xn minus A is less than this positive number. From here, it follows that Xn is less than C. Similarly, there exists N2 such that for any N greater than N2, the same statement about the sequence Yn. Yn minus A, minus B, not minus A, minus B. Minus B less than positive number B minus C. And from here, it would follow that Xn is strictly greater than C. Not Xn, Yn. Then taking then for any N greater than maximum of N1 and N2, which I will call N, it follows that Xn is strictly less than C, which is strictly less than Yn. Hence, Xn is strictly less than Yn. End of proof. Any questions? Next theorem, theorem 4. In English literature, this is called a sandwich theorem. In Russian literature, it is sometimes called a two policeman theorem. I will call it neutrally a theorem about three sequences. So, suppose sequences xn, yn, and zn such that for any n xn is smaller than yn, which is smaller than zn. Actually, we can use less or equal. Yes, less or equal. If sequence xn and sequence zn both converge to the same limit then yn also converges to this same limit a, to the same limit, to the same number a. So basically, like geometric interpretation is those two sequences like squeeze this middle sequence, and if those two sequences both converge to the same point, they like lead this middle sequence to that same point. That's why it's called a two policeman theorem, because if we have two policemen that held a criminal in between them, and they both policemen go to a police station, then the criminal will also end up in the same place, same police station. Okay, now let's prove it. Proof. Given epsilon greater than 0, let's choose n1 and n2. Such that for any n greater than n1, a minus epsilon less than xn less than a plus epsilon, and for any n greater than 2, a minus epsilon less than zn less than a plus epsilon. So here I'm writing down the definition of a sequence xn tending to a and sequence zn tending to a. It says for any epsilon greater than 0 there exists capital N1, such as this bit, and the second definition the same about this bit. So we just wrote down two definitions. Very well. Then for any n greater than maximum of n1 and n2, which I'm going to call capital N, it follows I'm looking at this bit, writing this bit down, a minus epsilon less than xn. Then we know that for any n at all and for any term of our sequence, xn is less than yn, less or equal, which in term is less or equal than zn, which is less by virtue of this bit over here than a plus epsilon. Now let's look at this bit. a minus epsilon less than yn less than a plus epsilon. From here it follows a minus epsilon less than yn less than a plus epsilon. Very well. Then for any positive epsilon we found a number capital N such as for any small n greater than this number, this inequality holds. This is by definition a limit of yn being number A. End of proof. Any questions? Okay, from those two last theorems, I can write down a corollary, which would look like this. Corollary. Suppose xn tends to A, yn tends to B. A. If for any n xn is greater than yn, then A is greater or equal than B. B. If for any n xn is greater or equal than yn, then A greater or equal than B. C. If for any n xn is strictly greater than B, then A is greater or equal than B. D. If for any n xn is greater or equal than B, then A is greater or equal than B. Yeah, guys, look, we have different conditions, but the same result. A greater or equal than B. It could be equal to B. Okay, we are out of time, but I will just quickly say that those two first statements could be proven from the theorem 3 by contradiction, and the second two cases, C and D, could be proven by the same way, choosing yn equals just B. For any n, yn equals B. Stationary sequence. Okay. Thank you for your time. If you have any questions, please ask. Otherwise, goodbye.